A magnitude 4.2 earthquake is the kind of thing most Californians sleep straight through. It rattles a few windows, knocks a coffee mug off a shelf, and by lunchtime, nobody's talking about it. So why are seismologists staring at this one on the USGS earthquake map like it actually means something? Because of where it hit. This 4.2 didn't strike some random patch of desert. It struck the exact seam where the San Andreas Fault and the Garlock Fault cross each other in Southern California, a junction that has stayed quiet at this size for more than 26 years. Two of the most dangerous faults on the continent meet at that single point. And that point just moved. Stay with me, because by the end of this, you're going to understand why the smallest earthquakes sometimes carry the loudest warnings, and why this one has people who study the ground for a living paying very close attention. Let's start with what actually happened. On July 12th, the ground broke near Fraser Park, a small mountain community tucked up in the Tejon Pass, where Interstate 5 climbs out of the Los Angeles basin and over the mountains toward the Central Valley. If you've ever driven the Grapevine, that white-knuckle grade where the freeway snakes up through bare golden hills, you've driven right over this fault system without knowing it. The quake registered magnitude 4.2 at a depth of about 13 kilometers, which is a classic shallow crustal earthquake, right in the zone where California's faults do their real damage. Pull up the USGS latest earthquakes map and you can see it sitting there, a single dot in a stretch of mountains north of the city. Now look closer at those mountain ranges on the satellite view. Those ridges aren't random. They trace the faults directly. Giant scars carved into the landscape by millions of years of grinding rock. And running right through the middle of that dot is the line where the San Andreas and the Garlock come together. Look at the Did You Feel It map and you can watch the shaking spread out in colored rings across the region. In general, this was light to weak shaking, the kind people notice, but that doesn't topple anything. Residents in the mountain communities felt a sharp jolt. Down in the valley and out toward the desert, people reported a brief rumble, a rattle of dishes, a swaying light fixture. Nothing dramatic. Nobody was hurt, and that's exactly why almost every news outlet ignored it. But here's the thing that makes a seismologist's stomach tighten. A 4.2 is small, but it is precise. It landed almost exactly on the fault plane, at the meeting point, in a spot that the modern instrumental record shows has been essentially silent at this magnitude for the entire 21st century. So the question stops being how big was it? The question becomes why here and why now? And to answer that, you have to understand the two faults shaking hands at this junction. Zoom all the way out for a second, because it helps to understand why California is built this way. Almost the entire surface of the Earth is broken into giant slabs of rock called tectonic plates, and they're all slowly drifting, driven by heat churning deep inside the planet. Most of California, and the whole West Coast, sits right on the boundary between two of them, the Pacific Plate and the North American Plate. These two plates aren't crashing head-on and they aren't pulling apart. They're grinding past each other sideways, and the San Andreas is the master crack that marks the seam. This is not a temporary situation. It's been running for millions of years, and it will keep running for millions more, whether we like it or not. The city of Los Angeles is very slowly creeping northwest toward San Francisco, a few centimeters every year, and in tens of millions of years, they'll be neighbors. So earthquakes here aren't a freak accident or a sign of the end of the world. They're the routine, unavoidable heartbeat of a living plate boundary. The rock stores strain, the rock releases strain, over and over, forever. The only real questions are where the next release happens, how big it is, and whether the people living on top of it are ready. And that brings us right back to two specific faults doing the sliding at this one dangerous junction. First, the San Andreas. This is the famous one, the roughly 800-mile crack that runs almost the entire length of California, the boundary where the Pacific Plate slides north past the North American Plate. It's a right lateral strike-slip fault, which sounds technical, but is simple once you picture it. Stand on one side, look across, and the other side moves to your right. The two plates glide past each other horizontally, grinding at an average rate of a few centimeters a year, about as fast as your fingernails grow. That doesn't sound like much, but run it for 100 years and it adds up to meters of pent-up movement. And here's the catch. The fault doesn't slide smoothly. It locks. Friction welds the two sides together while the plates keep pushing. So the rock on either side bends and strains and stores energy like a drawn bow, year after year, decade after decade. Then one day the friction loses, the fault snaps, and all that stored energy releases in seconds. Geologists call this elastic rebound, and it's the beating heart of every major earthquake. When the southern San Andreas finally rebounds along its full length, it is capable of a magnitude 8 or greater. That is the earthquake California has been dreading for over a century. Then there's the Garlock. Outside of geology, almost nobody has heard of it, and that is exactly the problem. The Garlock Fault cuts east to west across Southern California, meeting the San Andreas at this junction and running out toward Death Valley and the eastern Mojave. It's a left lateral strike-slip fault, the mirror image of the San Andreas. Look across it, and the far side slides to your left. And here's the part that should get your attention. The Garlock is heavily locked. The Paleoseismic record, The trenches geologists dig straight across the fault to read its rupture history in the layers of buried soil shows that Garlock has produced enormous earthquakes in the past, ruptures that shoved the ground 2 or 3 meters sideways in a single violent moment. But it has not had a major rupture in the historic period. Depending on which segment you look at, the last big one may have been somewhere between 500 and 1,000 years ago. That fault is capable of a magnitude 7.5 or greater, and it has been quietly winding up like a spring for centuries, with almost no one watching it. So now hold both of those in your head at once. A right lateral monster that can hit an 8, and a left lateral giant that can hit a 7.5, both loaded with strain, crossing each other at the precise spot where a 4.2 just fired off. That is the setup. But it gets more interesting and more unnerving when you look at the shape of the fault right at the junction. Look at the San Andreas on any geologic map, and you'll notice it doesn't run in a clean straight line through here. It bends. Right at this region, the fault swings into a long sweeping curve that geologists call the Big Bend. And bends and strike slip faults are where the real trouble lives. When two plates are trying to slide straight past each other, but the fault forces them around a curve, the rock can't glide cleanly anymore. It jams. It compresses. This is what's called a restraining bend, and instead of releasing sideways, the crust gets squeezed and shoved upward. That squeezing is literally why the mountains are there. The entire chain of the transverse ranges, those east-west mountains around Los Angeles that run the wrong way compared to most of California, was pushed up by the compression at this bend. So every ridge you see in that satellite view is a monument to strain that has nowhere to go. And strain that has nowhere to go doesn't disappear. It accumulates, and it accumulates, until something finally gives. The Big Bend is one of the most strained sections of the entire San Andreas system, and it sits directly on top of the Garlock Junction, a locked fault, meeting a bent fault, feeding a mountain range, all at one point. And that point is where the ground just moved. Now, if this junction were sitting there calm and quiet, a single 4.2 might be background noise, but it isn't calm. Because 6 years ago, something happened just to the east that shoved this whole system closer to the edge and outside the seismology world. Almost nobody understood the significance. In July of 2019, out in the Mojave near the town of Ridgecrest, the ground tore open. It started with a magnitude 6.4 foreshock on the 4th of July, strong enough on its own to make national news, cracking roads and starting fires. But that was just the opening act. The very next day, the fault unleashed a magnitude 7.1, the strongest earthquake to strike California in more than 20 years. The Ridgecrest sequence buckled highways, ruptured the desert floor, and left surface scars you could see from space, long gashes where the earth had simply slid apart. And then the seismologists ran the numbers on what that earthquake did to the faults around it, and the result was sobering. When a big earthquake ruptures, it doesn't just release stress, it transfers it. The crust is all connected, and when one giant block lurches, it shoves and pulls on its neighbors, loading some faults and unloading others. This is called Coulomb stress transfer, and it's one of the most important ideas in modern earthquake science. The calculations from the USGS and independent researchers showed that the Ridgecrest earthquake increased the stress on the Garlock fault by roughly 30%. 30% on a fault that was already locked and loaded after centuries of silence. So think hard about what that means. The Garlock was already one of the most dangerous quiet faults in North America. Then Ridgecrest came along and cranked the tension up by nearly a third in a single week. And this isn't just math on a whiteboard. In the months after Ridgecrest, satellite measurements actually caught the Garlock fault beginning to creep, showing real, measurable movement along tens of kilometers of a fault that had shown almost nothing in the modern record. The fault physically responded. The spring wound tighter. The trigger got lighter. And now, years later, a 4.2 fires off at the far western end of that same loaded system, right where it kisses the San Andreas. Coincidence is possible, and I'll always tell you when something might just be chance. But this is the kind of coincidence that makes you sit up straight. Now, you might be wondering how anyone can possibly know that a fault gained 30% more stress, or that the Garlock started creeping. We're not guessing, and this is where modern earthquake science gets genuinely impressive. All across California, there's an invisible nervous system of instruments watching the ground every second of every day. There are thousands of seismometers buried in the crust, sensitive enough to feel a truck rumble by or a tremor on the other side of the planet, and they triangulate the location, depth, and magnitude of every quake within seconds. There's a dense grid of GPS stations, the same satellite technology in your phone, but accurate down to the millimeter, bolted into bedrock to measure the plates physically bending and straining in real time. And there are radar satellites doing something called INSAR, bouncing signals off the ground on repeat passes to map how the entire surface of the state deforms, centimeter by centimeter, painting pictures of exactly where the crust is squeezing and stretching. So when I tell you the Garlock crept after Ridgecrest, that's not a hunch. Satellites and ground stations physically watched it move. That web of instruments is also how we know this junction has been silent for 26 years, and it's how we'll get the first warning if the ground here ever starts to accelerate. The faults are being watched more closely than ever in human history. The problem was never seeing the earthquakes. The problem is that the Earth doesn't announce the big ones in advance. To really feel the weight of this, you have to look at the ghosts. Because this junction has a history, and the history is genuinely frightening. Rewind to January 9th, 1857. The southern San Andreas ruptured in what we now call the Fort Tejon earthquake, a magnitude 7.9 that tore the ground for well over 200 miles. The shaking lasted somewhere between 1 and 3 minutes, which is an eternity when the world is trying to throw you off your feet. There's an account from a man named Sylvester, who described the ground moving in visible waves, like the surface of the sea rolling across solid land. Rivers were thrown clean out of their beds. The Kern River was reportedly tossed so hard that fish were left stranded on dry banks. And along the fault, the two sides of the earth slipped past each other by as much as 9 meters. You can still go out to a spot called Wallace Creek today and see where the stream bed was violently offset, frozen in the landscape as a permanent record of that day. The epicentral region of that monster sits right up here, near the same big bend, near the same junction we're talking about. That was the last full rupture of this section of the San Andreas. It happened over 160 years ago, and the fault has been silently reloading every single day since. And here's why that number should stick with you. When geologists trench across the southern San Andreas and count the ancient ruptures buried in the soil, they find this stretch tends to break roughly every 1 to 200 years on average. We are now deep inside that window. The fault isn't just quiet, it's arguably running late. Every year that passes without a rupture isn't a year of safety. It's another year of strain packed into the same locked rock, waiting. Go back a little further, to December of 1812, and you find another violent chapter. A major earthquake struck the region, and the sequence included a double punch, one large shock followed by another. One of them hit hard enough to collapse the church at Mission San Juan Capistrano during morning services, killing dozens of worshippers under the falling stone. For its time, in a sparsely populated Spanish California, that was a catastrophe, and it's a grim reminder that these faults have killed before, in living memory of the buildings that still stand today. Then come forward to July 21st, 1952. The Kern County earthquake, a magnitude 7.5 on the White Wolf Fault, ripped through the mountains just to the north of the junction near Tehachapi at a depth of about 6 kilometers. It was one of the largest earthquakes to hit California in the 20th century. It cracked tunnels, twisted rail lines into ribbons, and killed a dozen people. And while it didn't rupture exactly on the junction, it was close enough and tangled up enough with the same web of faults to prove this region can still produce genuine disaster in the modern era. Now, if you plot all of these events on a map, something eerie emerges. Fort Tejon to the north and west. The 1812 events down toward the coast, the 1952 rupture just to the north. They frame the junction on almost every side, like footprints circling a single spot where nothing has stepped in a very long time. The junction itself, the exact seam where the 4.2 just hit, is the quiet center of a very loud neighborhood. And quiet centers and loud neighborhoods are exactly what seismologists lose sleep over. Here's something that turns this from an abstract science story into something that could reach into your daily life, even if you live nowhere near the fault. That junction at Tejon Pass isn't just empty mountains. It's one of the most critical infrastructure choke points in the entire state of California. Interstate 5, the main artery connecting Los Angeles to the rest of the country, crosses the San Andreas right here. The California Aqueduct, the vast concrete river that carries a huge share of Southern California's drinking water down from the north, crosses the San Andreas here too. Major natural gas pipelines cross it. High-voltage power transmission lines cross it. Fuel lines that keep Los Angeles running cross it. Everything that feeds a megacity of millions of people funnels through this narrow mountain pass, and it all has to leap over the same fault that produced a magnitude 7.9 in 1857. So imagine a major rupture at this junction. It wouldn't just shake buildings. In one motion, it could sever the water, the fuel, the power, and the primary highway into Southern California, all at the same time, all at the same place. That's not a fringe fear. That's the exact scenario emergency planners wargame, because the geography forces every lifeline through the one spot with the worst possible history. So when the ground moves at this junction, even a little, it's worth understanding, because the stakes here are wired directly into everyday life for millions of people. If you're finding this useful, take a second to hit subscribe. I break down earthquakes and seismic risk across California and around the world almost every single day, and this is a story that is still unfolding in real time. All right, let's get into why the specific 4.2 broke a silence that had held for decades, and what the science really says about small quakes at loaded faults. Here is what the instrumental record shows for this precise section of the San Andreas, where the Garlock meets it. Over the past 26 years, going all the way back to the start of the 21st century, you can count the earthquakes that have struck this exact junction on very few fingers. There have been rumbles to the south of the Y-shaped intersection. There have been rumbles to the north. Sort the historic seismicity by magnitude, and you'll find a couple of 5s scattered across the wider area. A 5.2 here, a 5.1 there, along with a handful of 3s creeping up over the years, but almost none of them land on the junction itself. This 4.2 is essentially the only earthquake of its size to strike directly on the meeting point in the entire modern record. And a 4.2 is not a 3. The magnitude scale is logarithmic, which trips people up constantly, so let me make it concrete. Every whole number up is about 32 times more energy released. So a 4.2 isn't slightly bigger than a 3, it's many times bigger. And the 7.5 the Garlock can produce isn't a bit bigger than this 4.2. It's on the order of tens of thousands of times more energy. The difference between a firecracker and a warehouse of dynamite. That's the gap between what just happened and what this fault is capable of. So a 4.2 is a real crack in the crust, not a whisper. Even if it's a long way from the monster the fault could unleash. So when a fault segment that has been dead quiet for a generation suddenly produces its largest tremor of the century, right at the most mechanically loaded point in the system, that is not noise. That is the fault clearing its throat. Seismologists have a name for a stretch of a major fault that has stayed quiet while everything around it moves. They call it a seismic gap. The idea is that if a fault is known to rupture, and every section around a particular segment is broken, but that one segment hasn't, the quiet segment isn't safe. It's overdue. It's storing the energy the others already released. This junction, framed by 1857 and 1812 and 1952, but silent at its core, has the fingerprint of exactly that kind of gap. And a fresh 4.2 waking up inside a seismic gap is precisely the sort of thing that gets circled in red. Now, I have to be honest with you about foreshocks, because credibility matters more than drama. Does a 4.2 mean the big one is coming tomorrow? No. Here's the real science. Only a small fraction of earthquakes, somewhere in the range of 5 to 10%, turn out to be foreshocks to something larger. The overwhelming majority of small tremors release their little bit of energy and the fault simply goes quiet again. And here's the frustrating truth. We can almost never tell the difference in advance. A foreshock and an ordinary small earthquake look identical when they happen. It's only after a bigger one strikes that we look back and say, that little one was a warning. So I'm not going to stand here and tell you this 4.2 is a foreshock, because nobody on Earth can know that yet. What I can tell you is that it raises the odds, at least a little, and that a small quake at a critical stress point deserves attention that its magnitude alone would never earn. That's the honest version, and the honest version is scary enough without any exaggeration. Because here's the part that pushes this from a shrug into a genuine watch this closely situation. This junction isn't waking up alone. The entire western edge of the North American plate has been unusually active, and the activity forms a pattern that stretches hundreds of miles. Start up in Nevada, just outside Reno, where a magnitude 5.7 struck near Silver Springs in April. That might sound irrelevant to California, but it isn't. That earthquake happened inside the Walker Lane, a broad belt of faults running along the eastern base of the Sierra Nevada. The Walker Lane is quietly taking up a growing share of the movement between the Pacific and North American plates, the same tectonic engine that drives the San Andreas. You can trace it on a map by following the string of desert lakes east of the mountains. Some geologists think the Walker Lane may represent where the plate boundary is slowly migrating over geologic time. So when the Walker Lane moves, it's not a sideshow, it's part of the same system rebalancing, and it changes the stress picture for everything to the west. That's part of how California unlocks. Then come to June, and an earthquake that genuinely caught the experts off guard. A magnitude 5.6 struck between the towns of Ukiah and Willits, up in the redwood country of Northern California near Redwood Valley. Why does that one matter so much? Because as far as the historic record goes, back more than 100 years, that region simply does not produce earthquakes of that size. This was new movement in a place that normally shows almost none, and when you overlay the fault maps, you find this 5.6 sits right where the San Andreas system undergoes another one of its major bends, up north this time. Turn on the historic 4s and 5s in that area, and a line of earthquakes appears, cutting straight across, separating one mountainous block from another. The crust up there is shifting into a new arrangement. Blocks that used to sit still are starting to grind, and that is exactly the kind of signal that says the whole plate boundary may be reorganizing at once, top to bottom. And it doesn't stop there. Back in December of 2024, a magnitude 7 struck just off the Mendocino triple junction, the wild tectonic knot off the far north coast where three plates collide and the San Andreas hands off to the Cascadia subduction zone. And that word, Cascadia deserves a pause. Just north of that triple junction lies the Cascadia subduction zone, a completely different kind of fault running from northern California up past Oregon and Washington. Where the San Andreas grinds sideways, Cascadia has one entire plate diving underneath another, and that geometry is capable of a magnitude 9, a continent-scale megaquake with a tsunami to match. The last full Cascadia rupture struck in the year 1700, and it too is considered overdue. So the far north coast isn't just another dot on the map. It's the doorstep of the most dangerous fault system in the lower 48, and it's been rumbling. Big Seven's hit the triple junction from time to time, so on its own that M7 isn't alarming. But stack it on top of everything else, and the picture sharpens fast. Nevada is moving. The far north coast is moving. The northern bend near Ukiah is moving in ways it never has in recorded history. And now the southern junction, the Garlock and San Andreas seam, has produced its largest tremor of the century. From the Mexican border to the Oregon line, the plate boundary is flickering awake on the map like a circuit board powering up. That is the context this 4.2 lives inside. And when you zoom out even further, past California entirely, it gets stranger still. There's a phenomenon in seismology that you rarely hear about, and it's the reason I always keep an eye on earthquakes that happen far away from California. When a large earthquake ruptures, the seismic waves it sends racing through the planet can load stress onto distant faults hundreds or even thousands of miles away. We already saw a static version of this with Ridgecrest loading the Garlock, but there's also a dynamic version where the actual passing waves from a distant quake nudge a faraway fault as they roll through. There's a famous case from 1992 when the magnitude 7.3 Landers earthquake struck the Mojave Desert. Seismologists watched it set off tiny earthquakes almost instantly at faraway spots, including up at Yellowstone and along faults hundreds of miles from the epicenter. The shaking waves themselves reached out and tickled distant faults into slipping. So the idea that a big quake in one place can influence faults far away isn't fringe speculation. It's observed, documented behavior. Faults sometimes fire in sequences across a continent, almost as if they're talking to each other through the crust. The classic example is the winter of 1811 and 1812. Out in the middle of the continent, along the New Madrid seismic zone in what is now the central United States, a series of colossal earthquakes struck, among the largest ever recorded east of the Rocky Mountains. They rang church bells hundreds of miles away in cities like Charleston. Eyewitnesses said the Mississippi River appeared to run backward as the ground heaved. And right in the middle of that eastern sequence, that very same winter, California had its own violent 1812 events near these southern faults. Two completely different parts of the continent convulsing in the same season. Was it connected, or was it chance? We honestly don't know for certain, and anyone who tells you they're sure is overselling it. But the pattern of clustered global seismicity is real and documented. And it's one more reason to watch the whole board instead of just one square. Now bring it right up to the present, because the planet has been loud lately. A devastating double earthquake struck along the Balcano Fault system in Venezuela, one large shock followed by another, and the destruction was catastrophic, with thousands confirmed dead and many more still missing in the rubble. There was a magnitude 6 down in Baja California, and there's a documented connection between earthquakes in Baja and later activity further up into Southern California. Not every time, but often enough that seismologists note it. There was even significant seismic energy in the Gulf and near Cuba, felt across Florida, in a region that almost never produces earthquakes that size. So step all the way back and look at the whole scene at once. Distant faults releasing enormous energy, a global uptick in large earthquakes, and California's own plate boundary flickering awake from end to end. Into that already tense environment drops a 4.2, precisely on the Garlock and San Andreas junction. In isolation, forgettable. In this context, it's a single data point that fits a much larger, much more unsettling pattern. Let's get technical for a moment, because the character of this 4.2 tells its own story. When seismologists analyze an earthquake, they don't just measure how big it was, they work out the focal mechanism, the precise geometry of how the rock actually moved, and they draw it as a little diagram everyone in the field calls a beach ball, a circle split into shaded and white quarters that encodes the direction of slip. For this 4.2, the beach ball came back as a strike-slip earthquake with a component of normal, extensional motion mixed in. Translation. The dominant motion was the horizontal grinding you'd expect from either the San Andreas or the Garlock, but there was also a bit of stretching, a slight pulling apart of the crust at that point. Now here's where the junction makes it genuinely ambiguous. The San Andreas is right lateral, the Garlock is left lateral. They are mechanical opposites, and because this quake landed right at the meeting point, we can't cleanly assign it to one fault or the other from the motion alone. But that extensional component is a real clue. It tells us the crust at the junction is being worked in more than one direction at once, which is exactly what you'd expect where a locked left lateral fault is shoving into a bent right lateral fault. Picture the Garlock pressing westward into the San Andreas. That pressure is part of what bows the San Andreas into its big bend in the first place. The 4.2 is a tiny expression of those competing forces finally slipping just a little at the seam, and any time a locked, loaded fault junction shows fresh slip, it deserves a much harder look than its magnitude alone would ever justify. Now, I want to talk about something more speculative, and I'm going to be completely straight with you about it, because I'd rather keep your trust than chase a spooky angle. In the hours before this 4.2, the sun fired off a solar flare, a magnitude M1.2 event, which is the second strongest category of flare. It triggered a radio blackout on the opposite side of the planet, over India and the Middle East, which happens to be roughly the far side of the globe from California. The timing was tight, just hours before the ground moved. Some people in the earthquake-watching community track these correlations closely. They look at solar flares, planetary geometry, even the position of Mercury passing between the Earth and the Sun, and they argue there's a relationship. And I'll be honest, the timing is close enough that I understand why people notice it. But here's what I owe you as someone actually trying to understand this. The mainstream science does not support a causal link between solar flares and earthquakes. The USGS has studied this question directly, and the established position is that there is no reliable correlation between solar activity, planetary alignments, and the timing of earthquakes. The energy from a solar flare, while staggering on the sun itself, is not delivering meaningful mechanical stress to a fault sitting 13 kilometers underground on the far side of the Earth. So I am not going to tell you the sun caused this earthquake, because the evidence simply doesn't support that claim, and I won't pretend otherwise to make a better story. What I'll say is this. It's an interesting coincidence in timing, worth noting and worth keeping an eye on, and nothing more than that. The real, testable, physics-based story here is the tectonics. The loaded Garlock, the bent San Andreas, the stress dumped on by Ridgecrest, the whole plate boundary waking up. That's where the actual signal lives. And that signal is strong enough on its own that we never need to reach up to the sky to explain why this junction has earned our attention. So, what does all of this actually mean for the next big earthquake in California? Let's walk through the real scenarios, from the most surprising to the most overdue, and be clear-eyed about each one. Scenario 1 is the Garlock surprise. Everyone in California braces for the San Andreas, because that's the famous name, the one from the movies. But the Garlock is the loaded gun nobody's watching. It's locked. It's centuries overdue. Ridgecrest just cranked its stress up by nearly a third and set it creeping. And now the junction at its western end is slipping. It is entirely possible that the next major Southern California earthquake ruptures the Garlock first, blindsiding almost everyone, precisely because it's not the fault people fear. A Garlock rupture could reach 7.5 or greater and would hammer the Antelope Valley, the high desert, and the northern edges of the Los Angeles region. And because the Garlock ties directly into the San Andreas, a big Garlock rupture could hand a fresh shove of stress straight to the San Andreas next door. Scenario 2 is the southern San Andreas itself. This is the classic nightmare, the full rupture of the exact section that last broke in 1857. It has been reloading for over 160 years. It can produce a magnitude 8, and it runs straight through the Big Bend at this junction, right past the aqueduct and the freeway and the pipelines we talked about. Emergency planners have actually modeled this in detail. It's called the shakeout scenario, a giant study built by the USGS around a magnitude 7.8 rupture on the southern San Andreas, and the results are grim. The model estimated around 1,800 deaths, roughly 50,000 injuries, and something close to $200 billion in damage. And here's the detail that surprised even the experts. The biggest killer in the model wasn't collapsing buildings, it was fire. Hundreds of fires igniting at once from broken gas lines, while the water needed to fight them was gone, because the aqueducts crossing the fault had just been torn apart at the pass. The study estimated the region could be without reliable water for months, shaking lasting a minute or more across the entire Los Angeles basin. Freeways and rail lines cut where they crossed the fault. Aftershocks rolling on for a year. This is the one the whole state quietly prepares for. And this junction is where that scenario begins. Scenario 3, the one that keeps the specialists up at night, is a dual rupture. Because these two faults are physically joined at the junction, it is at least possible for one to trigger the other, either at the same time or in quick succession. I want to be honest that this is not the most likely outcome, but the direct mechanical link at this seam moves it out of the realm of science fiction and into the realm of things worth planning for. And then there's the north, because that 5.6 near Ukiah reminded everyone that Northern California is loaded too. If we're talking Northern California, the Bay Area is dramatically overdue. The Hayward Fault runs directly beneath densely populated East Bay cities like Oakland and Berkeley, and it has a history of rupturing on a roughly regular cycle. By that clock, it is past due. The Calaveras and Green Valley faults are ready to go. And here's the humbling part that should keep all of us modest. There are hidden faults we don't even know exist until they break. Back in 2014, a magnitude 6 struck Napa on the West Napa Fault, a fault that wasn't fully recognized as a major hazard before it ruptured, cracked roads, and started connecting the dots to the faults around it. The ground under California is laced with cracks we still haven't found. So when I look at this 4.2, I'm not seeing one isolated tremor in the mountains. I'm seeing one more signal inside a system that is clearly, measurably changing. Let me bring this all the way home. A magnitude 4.2 earthquake struck near Fraser Park at a depth of 13 kilometers, precisely at the junction where the San Andreas and the Garlock faults cross. Two faults that are both overdue for major earthquakes. The San Andreas capable of an 8 or greater, the Garlock capable of a 7.5 or greater. This junction sits at the Big Bend, one of the most strained sections of the entire fault system. The very compression that pushed up the mountains around Los Angeles. It was loaded further by the 2019 Ridgecrest sequence, which raised stress on the Garlock by roughly 30% and set it visibly creeping. It is bracketed by historic monsters, the Fort Tejon 7.9 in 1857, the deadly 1812 events, and the Kern County 7.5 in 1952. It's the choke point where the water, fuel, power, and main highway for millions of people all cross the same fault. And it just produced its largest tremor of the entire 21st century. At the exact moment, the whole Western Plate boundary, from Nevada to the far north coast, is coming awake. None of that guarantees a big earthquake is imminent. Small quakes usually stay small. But all of it together is why a tiny tremor at this one spot is worth a full, careful breakdown instead of a shrug. There is one piece of genuinely good news in all of this, and you should know about it. California now has an earthquake early warning system called Shake Alert. It works because that web of instruments detects the first, faster, gentler waves of an earthquake and races a warning ahead of the slower, destructive shaking that follows. Depending on how far you are from the rupture, that can buy you anywhere from a few seconds to more than a minute of warning before the ground where you're standing starts to move. A few seconds might not sound like much, but it's enough to drop under a table, pull your car to the shoulder, or step back from a heavy shelf. You can get those alerts straight to your phone through the built-in system or the free MyShake app. And if you live in California, turning that on today is one of the smartest 30 seconds you'll spend all year. And when the alert comes, or when you feel that first jolt, the advice from every expert is the same 3 words. Drop, cover, and hold on. Get low, get under something solid, and hang on until the shaking stops. Don't sprint outside, because outside is where the glass and the bricks come down on you. That one habit saves lives in every major earthquake. So here's what I actually want you to do with this, because information without action is just anxiety with extra steps. If you live in California, or honestly anywhere that faces natural disasters, build a plan before you ever need one. Put together a grab bag you can carry out the door in seconds, with water, basic supplies, and a way to stay informed when the power and the cell towers go down at the same time. A hand crank radio is one of the smartest things you can own for exactly that moment, because it doesn't care about the grid. Think about backup power too, something like a portable power station you keep charged in a closet, paired with a couple of foldable solar panels so you can pull energy straight from the sun if the grid stays dark for days. Know where your gas shutoff is. Bolt the tall furniture to the wall. Talk to your family about where you'll meet if the phones don't work. None of this is about living in fear. It's about being the calm, prepared person when the ground finally decides to move, instead of the one scrambling in the dark wishing you'd listened. I'll keep tracking everything happening at this junction and with seismic activity across California and around the world. As of today, that scene between the Garlock and the San Andreas has gone quiet again. But quiet is exactly how it always starts, and this fault has broken its silence in the most violent way imaginable before.